Good evening. This presentation has one objective only, and that is to familiarize you with the last vector quantity to which you'll be introduced this semester, and that is angular momentum. And if you're thinking, hey, does that have anything to do with regular old momentum, since the word momentum is in the name? And the answer is yes. We take the vector momentum and do one little thing to it to get this other quantity called angular momentum. And while it is a vector, we're really not going to use the vector nature of that quantity too much here because we kind of ran out of time. Same thing with torque. Torque is really a vector. We don't have to worry so much about the vector character of torque. So this little black dot, let me get the laser pointer. I always forget to get that ready. This little black dot represents a small mass, a point particle in the XY plane, and I've indicated its linear momentum with this red vector. Remember, you get the linear momentum by taking the velocity vector and scaling it by mass. So it points in the same direction as the velocity. So we know that this particle is moving directly left. And the length of this vector tells us something qualitatively about the product of mass and speed. So if this thing were more massive or moving faster, we would stretch that vector, because remember, the magnitude of momentum is mass times speed. Now, just like with torque, when you're calculating torques, you draw this vector r that goes from the origin to the point of application. I'm still calling the vector r here, but this is not the point of application of a force. It's the actual location of the particle at that instant in time. So it's the position vector r, which we've been using for a while. And now you see I've resolved the position vector into components. See how these two vectors, these dashed blue vectors, add up to the original vector r? And notice that the components are perpendicular. That's how you resolve a vector normally into components. And I'm going to call this component r perp, because you'll notice that it's perpendicular to the momentum vector. So one way to visualize angular momentum is to resolve the position vector of your particle into components, one of which is perpendicular to the momentum vector. Now, you may have to extend the direction of p in order to more easily see r perp. Here I didn't need to do that because I already drew the vector fairly long. Okay, so I've indicated this dashed line in the same direction as p. If you have to, go ahead and draw that line to help you visualize r perp. And here it is. We use the letter, it's pretty universal to use the letter L, not a capital L for loser, L for angular momentum. This time it makes a little bit of sense because there actually is an L in angular, even though there's no I in team or P in momentum. R perp P, that's it. Just take the linear momentum P, and that's got units of kilograms, meters per second, or what is it, Newton seconds? Yeah, Newton seconds is an alternative way to express the units of P, and then multiply that by distance. Simple as that. Now, a Newton second, when you multiply by r perp is a distance in meters. So Newton meters seconds is what you get. And we know that a Newton meter is a joule. So if you're a unit aficionado, that's maybe the nerdiest thing I've ever said, but Newton seconds are the units of momentum. Joule seconds are the units of angular momentum, joule seconds. Otherwise, you could just look at the quantity. It's meters, kilogram meters per second. R perp P, R perp P. Try to memorize that, R perp P. Here's just a couple more examples. In fact, these are related. See, if this particle continued to move in the direction it was already moving at the same speed, you see that in a moment it would be over here. So it's moving just as fast in the same direction. But I'm going to switch back and forth between the slides, even though the position vector r has changed. So the distance from the origin has gone down, but this perpendicular distance from the origin to the direction of P has not changed. Previous, now. Previous, now. R perp is the same. And that means that the angular momentum is the same. So is that true in general? I think that may be true in general, that a particle moving, yes, a particle moving in a straight line at constant speed actually has a constant angular momentum. Even though the position vector is changing, that quantity r perp does not change. So if there's no force on a particle, we know that it moves in a straight line at constant speed. Evidently, one consequence of that fact is that its angular momentum is unchanged. A moment later, it's even further to the left or farther to the left, still moving at the same speed. The position vector has changed yet again, but r perp is not. Again, same angular momentum, r perp p. Okay, how about something in circular motion? Because that shows up a lot, right? A particle on the wheel of a tire, a planet going around the sun, you going around the axis of the Earth on your diurnal rotation. That's a fun word for daily, diurnal. Okay, we know that for a particle in circular motion, the velocity is always tangent to the circle. But what other vector points in the same direction as velocity? That would be the linear momentum vector. You just scale the velocity by m. So the momentum vector is also always tangent to the circle. And maybe you recall from high school geometry, it was a long time ago for some of us, that the radius to the point of tangency is perpendicular to the tangent line. So the r vector here is already perpendicular to p. That makes it easy to calculate r perp. It's simply the radius. Now, as you watch the particle go around, if it's a circle, then the radius isn't changing. And if the linear momentum is constant in magnitude, and that's true if the speed is constant, then neither of these quantities changes. R perp is always just the radius of the circle, and p is just mv, where v is the speed that doesn't change in uniform circular motion. So even though the directions of r and p are changing, and that's different from before, right? Here, the direction of p didn't change as I went along these slides, but the direction of r did change. Now both vectors are changing positions as we go around the circle here, but the magnitude of p does not, and r perp does not. So evidently an object in uniform circular motion also has constant angular momentum. Now there's a caveat there, or I should really qualify that statement. Notice that we're computing the angular momentum about a particular point. It's just like torque. The value that you get for a particular torque depends on where you put your origin. Here, the origin is at the center of the circle. So the angular momentum about the center of the circle is constant for a particle in uniform circular motion. And I also want to take a moment here to talk about the sign, S-I-G-N, of angular momentum. I mentioned briefly at the beginning of this video that angular momentum is a vector quantity. Now, all the problems that we're going to look at from here on out, since we're just a few days from the end of the semester, involve really just one component of angular momentum. And that is coming out of the page or going into the page. So for a particle moving within a plane, all the pictures we're going to look at, it's motion within a plane. Even when we talk about the motion of a planet around the sun, we'll see that it's motion in a single plane. If that's the case, then the angular momentum vector points out of the page or into the page. And it's very easy to figure out which direction. First, just ask yourself, which direction is the particle moving? Is it kind of going clockwise around the origin or counterclockwise? Now, for this example, it's easy. It's going counterclockwise. So here's what you can do. And again, I know you're watching this not in a classroom, so it doesn't matter how goofy you look. Don't worry about your classmates seeing you do this. Take your right hand, smack yourself in the face with it for me. Okay, no. Take the fingers of your right hand and curl them in the direction that the particle is moving. See how the particle is moving off in this direction? So put the fingers, the forefingers, like the non-thumb fingers, in that direction. Or just curl your hand counterclockwise. And your thumb tells you that the angular momentum points out of the page. See that? Now, this previous example, this is not circular motion, but I mean, if you had to pick one or the other, counterclockwise or clockwise, it seems pretty clear to me that this particle actually is moving in a counterclockwise direction around the origin. So your thumb would also be coming out of the page. Now, just like torque, out of the page or into the page can be equally expressed as, or it can be expressed just as well by saying positive or negative, right? Out of the page, into the page, it's two options, clockwise, counterclockwise, positive, negative, however you want to do it. So just like in trigonometry in high school, we consider counterclockwise angular momentum to be positive. That would be out of the page. Okay, moving on. How about straight line motion again? Here's a particle, and it didn't have to stay in a straight line, right? previously I was considering something that was moving in a straight line, but this particle here, maybe there's air drag on it or an electric force on this particle if it's got electric charge, which you'll learn about in 3B. In that case, the particle would be accelerating. It would not be moving in a straight line, but we're just looking at one instant in time here. So I've drawn R, I've resolved it into at least the perpendicular component. And notice that in this instance, I did have to extend the P vector so that I could visualize R perp. And I would say that this is, if anything, it's counterclockwise motion about the origin. So the angular momentum would be coming out of the page. Now let's just imagine that this particle is moving in a straight, no, is that what I want to do? What's next? No, okay. So what if the direction of this particle's course is changed? It gets deflected, and now it's moving down in this direction. See how the direction of the velocity has changed? Look at what happened to R perp. It decreased. This was before, this is after. Now, if the particle is still moving at the same speed, and the mass is still the same, presumably, then the magnitude of P has not changed. The magnitude of P is just mv, where v is speed. So if you haven't sped up or slowed down, you've just turned, and your R perp decreased, then your angular momentum did change. The particle in this slide here has different angular momentum than it did in this slide. Now let's continue this this direction here. What if, because notice how from here to here, I tilted P towards the origin. What if I tilt it just a little bit more so that the velocity is actually pointed right at the origin? So this particle is on a collision course with the origin. If the origin were the sun, and this was a piece of space garbage, it would be on a crash course with the sun. And you see that R perp has now gone to 0. So it's a lot like torque. If the force vector, or if the line of action of the force passes through the origin, then we say the lever arm is 0, no torque, or the moment of that force about the origin is 0. Here we're not talking about torque, we're talking about angular momentum, but we see that if the P vector, not force, but P, points through the origin, then there's no R perp, and that means no angular momentum. So the particle does have linear momentum, but the value of its angular momentum is 0, specifically the angular momentum about this point. If we put the origin over here, then there would be an R perp. See that? The R perp would be something like that. So the angular momentum does depend on where you put the origin. So maybe you're wondering, what is even the point if it depends on where you put the origin? It's because in a lot of physics problems, there's a very natural choice of origin. Like when you're analyzing the motion of planets around the sun, the natural place to put the origin ends up being the sun. And that choice of origin makes it very easy to use angular momentum to derive some interesting results, like Kepler's laws, for instance, which we'll get to in the next chapter, hopefully. Okay, here's a particle that's, if anything, going clockwise around the origin, not counterclockwise. So again, do that thing with your right hand. This is called the right hand rule. There are many right hand rules in physics. This is one of them. If you curl your fingers clockwise to reflect the motion of the particle, do you see that your thumb is going into the board or into the page? We would consider that a negative angular momentum. And because P is long enough, I'm able to draw R perp without having to extend the direction of P. And now let's introduce this angle beta. Now, just like torque, in torque, we talked about the angle between the R vector, that's from the origin to the point of application of the force, and the force vector. And I think we used the Greek letter theta for that. Some books use phi. Your book is choosing to use a different letter in the calculation of angular momentum, just to distinguish this from torque, because it's actually pretty easy to get these all jumbled up in your head. Not if you've been teaching it many semesters like me, but if you're learning it for the first time, it's like formulas going in one ear and coming out the other ear. So let's use a different letter, beta. Beta is the angle between the R vector and the P vector. Now let's look at this right triangle that I've drawn, the right triangle that comes from decomposing R into components which are perpendicular and parallel to the P vector. And the original R vector, of course, is the hypotenuse. R perp is the side opposite beta. So if you take the hypotenuse R and multiply by the sine of beta, that should be equal to R perp. R perp is the same as R sine beta. Now remember, angular momentum can be defined as R perp P. So why don't we take this expression for r perp and plop it in right here, and we get another way of expressing angular momentum. You could say it's r sine beta p. And just like in toric, which was rf sine theta, let's put the r and the p together, and we'll write it that way. So you should also know this. Throw that on your note card, or even better, tattoo it on your brain. Memorize that. Rp sine beta, it's a lot like Rf sine theta. It looks like the formula for torque, but this is a new type of momentum. It's angular momentum. And maybe you can see why we call it angular momentum. It does involve an angle. Okay, so the comparison should help you remember the two. They're similar. Just remember, torque involves applying a force to something in order to get it to rotate. That's how you can remember that it's got an F inside the formula. Angular momentum obviously involves momentum, so it should have a P in the formula. Now, about this angle beta, I lied to you. Technically, I lied to you in the previous slide. Beta is really the angle that swept out from the r vector to the p vector. So these vectors have been drawn tip to tail, but if you put them tail to tail, so here's the tail of r, scoot r so that its tail is here, and r would go off in this direction. In order to sweep from r to p, from r to p would be this angle. That's really the angle beta, and you can assign a sign to that angle using the same rule that you learned in high school trigonometry. Again, you put your fingers along R first, the fingers of your right hand, and you curl them towards P. And you just ask yourself, did I have to curl my fingers clockwise or counterclockwise? Evidently, in this picture, we have to go clockwise to get from R to P. And so we consider beta to be a negative number. Technically, B would be negative. Now, what was I doing with this slide here? I had to scoot this over so you can see what happens next. Let me say one more thing about the slide, actually. If beta is negative, then when you go back here to this definition, isn't the sign of a negative angle also negative? As long as it's in quadrant 4, between 0 and negative 90. So that's another way of seeing that the angular momentum is negative. Previously, I said that if you have to curl, if you're looking at the direction that the particle is going, like in this case, it's clockwise, not counterclockwise, that would be an angular momentum that's negative. Well, you can get the same result by just asking what the sign is of beta, SIGN. Since beta is a negative number, then when you calculate the sign, SIN sign of beta, you will also get a negative number. Two different ways of concluding that this angular momentum is negative. Okay, so there's another way to think about the definition of angular momentum, and we're going to use that for something interesting towards the end of this video. So I was resolving R into components, one of which is perpendicular to P, and I call that R perp. Let's do something different. Instead of resolving R into components, let's resolve P into components. So I've made a right triangle out of the P vector, and then one of the components is parallel to R, and the other one is perpendicular to R, hence the name P perp, which is fun to say, P perp. Now, you can draw it this way, or you can draw it this way. See how these are equivalent? And I've identified this angle here as beta. Do you see how this angle and this angle are alternate interior angles? They have to be the same. So let's look at this right triangle now. How can we express P perp, which you'll notice is the side opposite beta? How can we express P perp in terms of P, the hypotenuse, and beta? Well, just like before, it's P sine beta, is it not? Hypotenuse times the sine of beta gives us the opposite side. So we've already seen this definition. I already used the R vector to show that angular momentum can be calculated as RP sine beta. Well, P sine beta can be rewritten as P perp. So here's another way of thinking about angular momentum. It's the magnitude of the position vector, the particle's position vector, times the perpendicular component of the particle's linear momentum. That works as well, RP perp or R perp P. So here are three different ways of calculating angular momentum. Which one should you use? Whichever one is easiest. In some problems, it's rather obvious what P perp is or what R perp is, and so you would go with the corresponding method of calculation. A lot of times, the r vector and the p vector are already perpendicular, which means beta is 90. What's the sine of 90? That's 1. So you just multiply r and p. Very simple. If those two vectors are perpendicular, it's trivial to calculate angular momentum. Have that on your note card, huh? At the very least, have this one. I'll try to find occasion to use this formula for some interesting stuff in chapter 13, when we look at the orbits of planets or satellites around the Earth, or Elon Musk's sports car that's going around the sun out at the distance of Mars, or whatever it was that he did. Okay, that was the angular momentum of a point particle. Everything we just looked at was the angular momentum for a point particle. You do need to know that definition. You need to know how to calculate a point particle's angular momentum. And if you're wondering, does this stuff get used for anything? Oh yeah, it gets used for all sorts of really cool stuff. Like I mentioned, you use it all the time when you're looking at the dynamics of a solar system, for instance. But believe it or not, angular momentum plays a really central role in the mechanics, or I should say the physics, of atoms and molecules. A lot of you have taken chemistry. You talked about energy shells, electron subshells, like the 1s level, the 2s and 2p. Can you have a 2d? I don't think you can. 3s, 3p, 3d. Well, guess what? Those letters SPD are distinguishing different quantities of angular momentum possessed by the electrons in their orbit of the nucleus. So angular momentum is all over the place in chemistry, whether you realized it or not. Now, at the level of the atom, it's a lot more abstract, because right now we're talking about particles moving around an origin. That's how they have angular momentum. If they were going through the origin, then r perp would be 0. But when you get to things like the electron, physicists discovered in the early 20th century that electrons can actually have angular momentum without orbiting anything. Like, they just have it. It's an intrinsic property of the electron. It's a rather abstract notion. So if you're going to study that stuff, you have to have a pretty good grasp on the classical angular momentum first. Okay, so we're talking now about a rigid object. And I should qualify right now, it doesn't have to be permanently rigid. Now, this is a wind turbine. You can see the 3 blades here. We do think of that as rigid. That thing's not supposed to bend too much or break. But the human body can also be thought of as rigid, because you can hold your body in a particular pose. If you jump off a diving board, you're in control. Well, I'm not, but some people are in control on the way down. You can pull yourself into a ball. You can do a pencil dive. So your body's flexible, but as you go from one posture to another, you can hold the posture and think of yourself as a rigid object. Okay, so basically, I'm saying we're not talking about a cup of water that you're sloshing around, and the shape of the water is obviously changing as you slosh it. We're not talking about Jell-O. I always use that Jell-O example. Got to come up with something better. A bowl of oatmeal, chocolate, yogurt. Oh man, I'm going to pause this video. I'll be back. No chocolate yogurt in the refrigerator. Okay, not only is this object rigid, it's rotating about a fixed axis, just like when we looked at torque equals I alpha. Remember, the assumption was that your truck wheel or your piece of pottery that you're shaping, whatever it is, it's rotating about a fixed axis, the gear in your machine. Same thing here. The axis obviously would be to the center of the turbine here. And we'll use the same device that we've used many times now this semester. We imagine that we've broken this piece of matter, I'm talking about the turbine, into a whole bunch of different little pieces. Maybe it's 1,000 pieces, 1,000,000, whatever. Not individual atoms, that's too overwhelming. So I'm going to call this piece M sub I, because if I've got 1,000 pieces here, I could label them M1, M2, M3, etc. This is M sub I. Maybe I is 500. And if this whole thing is rotating about a fixed axis, even though the turbine is not shaped like a circle, every point on the turbine is executing circular motion. Now, it may or may not be uniform circular motion. If the turbine's speeding up because the wind picked up, then it would not be uniform circular motion. This little piece of mass has a definite distance from the origin, which I'll call r sub I. Also, this is really the r vector. So I'm putting my origin on the axle of the turbine. And then since I imagined that this thing was turning clockwise, did I? Yeah, see the little clockwise arrows? Then this would be the direction of the linear momentum. And you'll see that I've drawn it tangent to the circle. And for this specific case, the r vector and the p vector are already perpendicular, which makes the calculation of this particle's angular momentum trivial. You would just take r times mv, where v is the speed of this particle. And notice I'm including subscripts on both of these vectors. This is the r vector for mass I. This is the linear momentum vector for mass I. Okay, and we've already seen the definition of a point particle's angular momentum. So L sub I is the angular momentum about this origin of just this piece of mass. I take r times p perp. So I'm using, instead of rp sine beta or r perp p, I'm using the rp perp definition, but notice it's rp perp for mass I, r sub I, p sub I, perp. So it's a little wordy here, but this is the perpendicular component of mass I's linear momentum. With me so far? No? Okay, well then go back in the video 10 seconds and rewatch. That's the beauty of this remote instruction, right? It's good and it's bad. I'm starting to wonder why did I never make these videos before? Because yeah, you got to put in the work to make the video, but once it's done, I don't have to stand in front of a board and deal with the markers that don't write. I just have to tap this arrow on the laptop, the lappy-toppy. Okay. What is linear momentum? It's mass times velocity. Now, in this presentation, I've been talking about p perp, the component of the momentum vector, which is perpendicular to r. But let's now borrow some language from chapter 8. Remember, in circular motion, your book likes to refer to the velocity as the tangential velocity because it's tangent to the circle. Now, maybe you're wondering, well, what's a non-tangential velocity? Because if you're moving in a circle, then that's your only velocity. Well, if you were spiraling outwards, you could describe the overall velocity as having a tangential component and an outward component along the position vector. So we're not going to mess with that. This is circular motion. Since momentum is mass times velocity, I just take the mass of the ith particle times its tangential velocity. Right? This together, mv tangential, is p perp. Different name, same quantity. And now we make a further use of some quantities that were introduced, I believe, in chapter 8, even chapter 4. And I can write the tangential velocity in terms of the angular velocity. Remember that? Arc length S equals r omega. Tangential speed vt is, wait, I misspoke. Let me back up. Arc length S is r times delta theta. R times angle is arc length. Tangential speed is r times angular speed. And then there's the other one, a sub t, linear tangential acceleration, is r times alpha. Well, we're talking about the speed here. So take any particle on this turbine, multiply its distance from the axle or axis times the angular velocity. Remember, this thing is rigid. I'm emphasizing down here is rigid. So every part of the turbine is turning together at the same RPM or radians per second. They can't be moving at different rotational speeds, because that would imply that the thing was breaking up. It would be breaking into pieces. It's a lot like the sun. Planet Earth, whether you're at the North Pole or the equator, it takes about 24 hours for you to turn once. But that's not so with the sun. I think the poles of the sun actually rotate more quickly than the equator. So the whole sun is kind of separating from itself in a way. It's more fluid. We're not talking about something like that. This is a rigid object. Okay. Can we simplify this? We've got an r here and an r here. Let's stick those together. And I'll put the r squared after the m very knowingly, because doesn't this set off some alarms in your head? Mr squared. What is that? Mr squared. Is that center of mass? No, center of mass is m times x plus m times x, etc. for each particle. Mr squared is rotational inertia. Aha. So this is the inertia of this, the rotational inertia of this single particle about the axis. We're going to use that in a moment. Okay, so what we've done now is expressed the angular momentum of just one piece of the turbine about the axis in terms of its mass, its distance from the axis, and the rotational speed of the entire turbine. And before we move on, let's ask ourselves, which direction does L point? Use the right-hand rule. If you curl your fingers in the direction that this particle is moving, which is clockwise, your finger would be pointing into the board or into the page. So L goes into the page. That's a negative angular momentum. And the same is true for every particle on this turbine. If you think about it, just pick another piece of the turbine, repeat the use of the right-hand rule, and you'll find that the angular momentum goes into the page. So since all these individual vectors, since the L vectors of each individual particle all point in the same direction, then to get the total angular momentum associated with the motion of this entire turbine, all we have to do is add those quantities up. Okay, so again, here's the angular momentum of the ith piece, L sub I. If we want the total angular momentum of this entire turbine, we just add up all the individual angular momentum. So sum over I of L sub I, that means L1 plus L2 plus L3, etc., all the way out to the last piece of mass. And I don't know why the typesetting changed here. See, I had the I underneath, and now it's in the corner. Sum up all your L sub i's. Well, here is L sub I. We just developed that formula. And I didn't write this out. See if you can do this in your head. This means this entire sum is M1 R1 squared omega plus M2 R2 squared omega plus M3 R3 squared omega plus dot, 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 dot for all the particles. Do you see how every term has an omega on the end of it? So let's just factor omega out from the entire thing. So in parentheses, you'd have M1 R1 squared plus M2 R2 squared plus all the way out to all the particles. Omega has been factored out, but aha, now we definitely recognize this. This is the prescription for calculating rotational inertia. Take every particle, multiply its mass by the square of its distance from the axis of rotation, add all those quantities up for every particle. That is the rotational inertia of the extended object. It describes the distribution of the mass, and we call that I suppose, for inertia. So there it is. L totes ma goats. If you want the total angular momentum of a rigid object, that's important, rigid object rotating about a fixed axis, it's I omega. I omega. Not I am the alpha and the omega. Sounds like that. I omega. You should try to memorize that. At the very least, throw it on your note card. I put a box around it. And do we really need the totes now? Let's just be concise. It's understood that L is the total angular momentum. You wouldn't use this formula for a point particle anyway, because a point particle doesn't really have a, when we think of rotational inertia, rotational speed, we think of something like a disk or a turbine, propellers on an airplane. Okay, so I've prepared this beautiful little table for you, comparing and contrasting useful quantities for point particles and extended objects which are rotating about a fixed axis, because the comparisons here should help you remember everything. F equals ma is the main dynamical result we've been using throughout the semester. And we used F equals ma to synthesize this other result, which is only applicable to rigid objects rotating about fixed axes, right? Can't use this for Jell-O or a pizza dough that's stretching. You can't even use it for like a protoplanetary disk. That's an early solar system where all the gas and dust spanning, a light year across in diameter is slowly contracting under the influence of gravity. That's not rigid either. You can't use this equation. But if you're talking about a vehicle's wheel or a ball rolling down a ramp, the sort of things we talk about in this class, then go for it. Torque equals I alpha. You've seen this for a while now, the kinetic energy of translation for point particle. Now, if you're talking about something spinning, I didn't put the K rotes here, but we are talking about rotational kinetic energy. You use the rotational inertia and the rotational speed to calculate the energy associated with the rotation of your mass. And lastly, momentum. We've got linear momentum and now angular momentum. But do you see the correspondence here? Instead of regular mass, regular inertia, we've got rotational inertia. M captures the resistance of an object to changes in velocity. That's one way to put it. I would say a more precise way is M tells you how difficult it is to accelerate something. I tells you how difficult it is to get something to rotate. So once again, M, how difficult is it to get something moving in a straight line? I, how difficult is it to get something rotating about an axis? All right, we're going to add one more formula to this table. Okay, L equals I omega. Let us take the derivative of both sides with respect to time. This must be headed somewhere interesting. All right, if both sides are equal, then their time rates of change should also be equal. And what can we do here? Right. I just realized there's a small logical inconsistency here. Yeah. Hang on a second. No, I'm not going to worry about that too much. Let's suppose that we are talking about a rigid object that's not changing its distribution of mass. So I'm not talking about a diver who's jumped off a diving board and they're pulling their arms and legs in. Let's go with one distribution of mass and stick with it, like the propeller on an airplane. And if that's the case, I is a constant. So we can pull it out in front of the derivative and then just take the derivative of omega. But now we recognize d omega dt. Isn't that's an acceleration, right? The rate of change of velocity. This is angular velocity. That would be an acceleration. We're looking at alpha here. D omega dt is alpha. So instead of I times d omega dt, I can write it as I alpha. And that should also set off some bells in your brain because we've been talking about torque equals I alpha. For a rigid object rotating about a fixed axis, torque equals I alpha. So we've got two equations now relating I alpha to something else. If these are both true, then we should be able to relate or to equate the left sides. They have to be the same. Torque must be the same as dl dt. So this is one of the most interesting equations in the entire semester. You can do some of the most interesting things with it. And unfortunately, we're not giving it its due here because it's really a vector equation. I've derived this for something laminar, you know, it's flat, it's spinning about a fixed axis. So we're not talking about like if you took a potato and chucked it in the air and it tumbled around and you could see its axis switching directions. I'm not talking about that, that's more complicated. But even in that scenario, this equation would still hold. So this is one of the most interesting equations in the whole semester. And you know, if you have the time, maybe go read the section in the chapter about precession. I'll point this out now. We ran out of time to cover precession. We're not going to cover it. There's a great Veritasium video about precession. Just type that in, P-R-E session, where he's got a bicycle wheel and he talks about some classic experiments. Anyway, that phenomenon requires the use of this equation. Okay, this one is also fairly easy to remember. Just think of the alternative statement of Newton's second law. Instead of F equals ma, force is the time derivative of linear momentum. And I pointed out this is really a better way to write F equals ma because it's still applicable even when you talk about particles moving close to the speed of light. That's the so-called relativistic domain. If you try to apply F equals ma in the relativistic domain, it doesn't work so well. But F equals dp dt does, provided that you define momentum properly. So instead of force being equal to the rate of change of linear momentum, we have a related quantity, torque. Torque requires force to calculate it. Torque is the time derivative of angular momentum. So if you can remember this one, you should be able to remember this one. Torque is analogous to force. Angular momentum is analogous to linear momentum. So I'll go back and throw that into the table. It's four pairs of equations that look very similar. Okay, now, let's take this up once again. And I realized I kind of cheated here because when I showed where this came from, that was back here. I pretended that I was a constant. So I pulled it out in front of the derivative. Well, now I'm talking about situations where I can change, where the mass distribution can change. So just, I guess you'll have to take it on faith that this equation can be developed even when the mass distribution is changing. It doesn't have to be the case that I is a constant. And if you think back to where I got this, it was remembering this equation, right? That's how I made the identification of torque with dl dt. Well, this equation came from a derivation where it's understood that torque is really the external torque. This tau represents the sum of all the external torques. Like if you're talking about a gear spinning inside a machine, we don't care about the torques between particles that belong to the gear. We're talking about torques from outside the gear, like another gear's teeth pushing on the first gear's teeth, or friction torque. It's the external torque. So the same thing has to be true here. It's really the external torque that we're talking about, or that we are talking about. So as an example, here's the object in question. Let's pretend it's this axle with the two gears on either end. That's our system. Well, there's going to be a contact force between the teeth of our gear here and the teeth of some other gear. That would constitute an external force and hence an external torque. The force is coming from outside the system. And I'm just looking at the direction here. If this thing is rotating counterclockwise, it's probably pushing that way on the teeth of this gear. And so you could use R and F to find the direction and magnitude of the torque on this bottom system here. Well, if there is a torque on this thing, then its angular momentum would be changing. That's what this equation says. If this number is not zero on the left side, if there is an external torque, then this number cannot be zero either because they're equal. Well, dl dt is the rate of L's change in time. And if that rate is not zero, that means that L is changing. If it has a non-zero dl dt, then it's changing. It's another way of saying it that this thing is going to start to spin faster or spin slower. That would change its angular momentum. Now, a lot of problems we look at are different. So isn't this cool? You can embed GIFs in PowerPoint. I hope it's actually working. It looks like, as seen from above, it looks like this football is spinning clockwise. Now, it's not hard to show that due to the symmetry of the football. So we're not talking about deflate gate, which might ruin the symmetry of your football, but for a symmetric football, there shouldn't be any net torque on the football. Gravity can exert torques on an object about its center of mass. Yeah, you know, that discussion gets a little complicated, but if this thing is just flying through the air while spinning, there shouldn't be any torques on it if you can ignore air drag. And if the left side of this equation is zero, there is no external torque, then that means that the rate of change of the angular momentum is zero. Now, we've been talking about the angular momentum of a laminar object, something flat spinning about an axis, you know, perpendicular to the page. This is a little different, but hopefully it seems plausible to you that this also has an angular momentum that would point either up along the axis or down along the axis. And here's another right-hand rule. It's similar to the one I've been talking about. Just take the fingers of your right hand, curl them in the direction that this thing is rotating, and your thumb points in the direction of L. So since I know that, as seen from above, this football looks like it's rotating clockwise, I'm curling my right hand clockwise. My thumb points down. That's how I knew to put the L vector in this direction. And presumably, as this thing is flying through the air after being thrown by somebody, the L vector would maintain its length and its direction. That's what the statement says. The L vector should be constant because there's no outside torque. Now, if you're thinking, wait, I've seen footballs wobble all over the place in flight. Like if you've ever seen me throw a football, that's probably what you saw. That's true. Well, in a more advanced mechanics class, you could analyze that and you would see that the wobbling might make this vector or this direction change. This is the axis of rotation. The axis of rotation might be precessing wildly, but you would find that the L vector actually is constant in time. And that's more complicated to visualize. Rigid body dynamics, that's a chapter in a more advanced mechanics class that's pretty mathematical. Okay, well, if this quantity L is not changing in time, then its value at time 1 is the same as its value at time 2, is the same as its value at time 3. So you could pick any two times. Here I've called those times T1 and T2. The value of L at time 1 must equal the value of L at time 2. And hopefully this is reminding you of momentum conservation, not angular momentum conservation, but regular old linear momentum conservation. That is what we're talking about. I didn't actually put that phrase on the slide here, but if L is constant, the fancy way of saying that is that L is conserved. If there's no outside torque, L is a conserved quantity. Well, if we're talking about a rigid object, remember, a rigid object rotating about a fixed axis this is our formula for angular momentum. I have to emphasize that repeatedly. You can only use this formula for L total, if you're talking about a rigid object rotating about a fixed axis of rotation. Okay, and I'm basically done here because this is the starting point for any problem involving conservation of angular momentum for a rigid object. And remember my qualification a little while ago, even the human body, while flexible and you can manipulate your posture, you can still hold that posture before and after. So we can still consider it a rigid object when you're holding that particular posture. So very often in angular momentum conservation problems, what you're doing is just solving for one of these four quantities. You would know the other three, you solve for the fourth. You have to recognize when it's valid to apply this principle. Not always. If there's a torque from the outside, it's not going to be valid. So the classic example is ice skaters. Pull up any physics book or video, and often they'll show you an ice skater spinning and pulling his or her arms in and spinning faster. I prefer to show the king of pop here. So are there any outside torques on MJ's body here? Well, when he's standing up on the balls of his feet, there's some friction between his shoes and the floor. But if you compute torques about that point of contact, I don't know how to pause this GIF, but look at the point of contact between his shoes and the floor. Put your origin there. And then what's the lever arm for those friction forces? Practically zero, because the forces are applied basically at the origin. So I would say that the moment of the friction force about his axis of rotation is basically zero. So you can say that the torque on his body about an axis through his center of mass should be zero. And that implies, if I go back here, that implies that his momentum at any time during the spin, his angular momentum at any time during the spin should be the same as the angular momentum of his body at any other time during the spin. So we can apply this equation, and I'm interested in solving for his final rotational speed. So this is, repeating ad nauseum here. You see that before he pulls his arms in, right there, he's got a certain rotational speed. It's not very quick. By pulling his arms in, what happens? The distribution of his body's mass about the axis of rotation changes. More of his mass, namely his forearms and his hands, more of his mass is now located near the axis of rotation. So he has reduced his rotational inertia about the axis through his center of mass there. And that means that this ratio is greater than 1. His initial rotational inertia was greater, that's before he pulled in his arms, was greater than his rotational inertia after he pulled in his arms. Okay, so you draw your arms inward, you reduce your rotational inertia, you would expect your rotational speed to go up. Okay, so all that's required to do something like this is to be able to balance, because if you pull in your arms, you're going to spin faster. It's just a fact of nature, consequence of angular momentum conservation. And there's some great other examples you can find. Go on YouTube. I should have had this video ready, but go on YouTube and find these videos of a bunch of teenagers on one of those carousels at the playgrounds. Not all playgrounds have them, but it's just a giant rotating platform. All these kids are on the outside. They get it rotating real fast, and then they pull themselves inward towards the center, and the whole thing rotates faster, and some of the kids get launched off. If you type in merry-go-round of, I don't want to say it because there's some idiots on YouTube who used a motorcycle to get the carousel spinning real fast. They put the tire, let me pause this is making me dizzy. They put the tire of the motorcycle, the front tire, on the carousel and spun the tire to get the carousel moving really fast. And it looks like nearly fatal for the people on the carousel. So I don't recommend watching that. It's kind of disturbing. But if you type in physics, merry-go-round of death, specifically angular momentum, you'll find some great demonstrations of this concept. Don't try it at home.